He said, "Oh, guys, look at my boyfriend." Boyfriend got me for a fucking cat with a name on it.
And I share the screen. Okay, so we are in business. Can you all see the screen?
You just think it's ridiculous shit. It makes you feel about yourself when you see somebody posts.
Wonderful. And I suggest we just simply ignore Stuart. That actually reminds me, does anyone have okay, good. It's all good. It's all good. So don't worry. Fantastic. Otherwise, I would have told you this really bad joke about the rabbit, but I'm not going to tell you now because all is good.
All is good.
Or is it? Yeah, it is. Good. Right. So please don't forget to register your attendance on Moodle. And I'm pretty sure that I can predict what's going to happen soon. Yeah, it's all right. No worries. We were quite interested in your private life, Stuart, so that's all good. Don't forget to register your attendance. And as I said, please complete the test because it will close, the program will close on, I think, next week, Tuesday. Yeah, I was just waiting for Bernardo to post the link. Don't become complacent. But I have to defend Bernardo. He already did earlier in the chat. So exactly, he already posted it. And thank you, Conrad, for posting it again. So everybody's in business. Excellent. All is good. So we don't have to worry about things. So what I want to do with you today is I want to carry on from where we stopped last time, that was yesterday, on first order reactions. And just as a quick recap, I showed you yesterday the equation for a zero order reaction. So zero order reaction, where we had the general rate law when we're looking at a reaction where the reactant A is consumed. We can write the general rate law dA over dt equals minus K times the concentration of A to the power of 0, which of course is the same as negative K, because A to the power of 0 is 1, and we don't have to write that. And we discovered that we can easily write this as the final concentration after a certain time equals the initial concentration minus K times T final minus T initial. And very often we will find that this T initial, when we start, that this is just simply 0, so we don't really have to take that into account. And we said if we want to plot some data sets, then we can do so very easily by plotting the time on the x-axis and the concentration of A on the y-axis, and we should get a straight line, something like that, where the gradient of this line would be negative k. We know that k is always a positive number. It can't be a negative number. It's always a positive number. And this point here, we said that was our initial concentration of A. So that's the initial concentration. And that's what we did yesterday. So quick question. If I extend this line, can it go into the negative range for a zero order reaction? Can it go into the negative area? Okay, yes, probably. What would that tell us? It would tell us here that if you look at that, our concentration of A in this area here, concentration of A would be smaller than 0. Concentration of A would be negative. Does that make sense? A negative concentration. Yeah, you're absolutely right, Reynolds. A negative concentration just simply does not make sense. And therefore, the concentration can only reach 0. A can only reach 0, but it can't get lower than that. Cannot get lower. Because a negative concentration simply doesn't make sense. So we need to be careful with that. We can also turn the whole thing around and say, if we have some data and we plot them in this way, where we plot the concentration of A versus time, and we get a straight line. If we get a straight line, when we plot concentration versus time, then we immediately know it must be zero order. Or in other words, if we plot concentration versus time and we get something like that, so A versus time, we get something like that, then we know it cannot be. This cannot be a zero order reaction, because it should be a straight line. And that's quite important when we look at some reactions later on. What would be a typical zero order? Where would we observe zero order reactions? Very often we will find that when we look at enzymes doing some reactions in cells, that very often we'll find that enzymes can work as zero order reactions. So enzymes can work under zero order conditions. Another one very often found is that elimination of drugs from an organism, this can follow a zero order reaction. And an interesting thing is that for example, in the elimination of alcohol from humans follows pretty much a zero order reaction if you are male. If you are female, the reaction is more complicated and the reaction scheme changes. I can't remember exactly what it is, but I think that's quite interesting. So males eliminate alcohol via a zero order reaction, whereas females have a slightly different process. So that's quite an interesting thing. Now, we then moved on and we discussed a first order reaction. First order reaction. And I'm fully aware of the conversation in the chat. So I've seen it and I will comment on that. So don't worry about it. So for the first order reaction, again, we have a reactant that is consumed. And we said we can write the rate law dA over dt equals negative K times concentration of A to the power of 1. And now we cannot just simply ignore this A as we've done with the zero order reaction. This A stays with us. I showed you how we can rearrange this equation, and eventually, after quite a bit of rearranging, we got the equation ln, the natural logarithm, A final over A initial equals minus K times T final minus T initial. That is basically the integrated form of this equation. And that's really the equation that I want you to remember. Of course, we can write this equation also in a slightly different format. We can write it as ln A final equals ln A initial minus K times, and for that I just simply set the T initial to 0. I just simply write this as T, and I've got a straight line equation, y equals C minus mx, or if I write it in a slightly different form, but I think you can figure that out. And if we try to plot that like this, we plot again time. And on the y-axis, we now plot ln of A. That's really important, ln of A. And we would get something like that. The gradient, again, that gives us negative rate constant, negative K. That's this bit here, M. This point here, what is that point, this blob? I asked you that yesterday. What is the blob? Absolutely right. Yes, that is ln, the natural logarithm of the initial concentration, lnAI. Absolutely right. And I think because I'm a really mean person, I left you yesterday with this sort of cliffhanger. What can it happen that this line goes into the negative range? Is this possible? Can it go into the negative range? What do you think? Anna says no. Katie says yes. Ah. Yes, for the drama. Right, let's think about it. Let's look at, let's say, this point here. This very clearly is a negative value. This is a negative value here, right? This cross. But this cross actually represents ln of a concentration. It doesn't represent the concentration. It represents the ln of a concentration. So let's, for example, let's put in here instead of, let's just put in a number which is smaller than 1. Let's put in, I just make something up, 0.1. So this point here would be ln of 0.1 molar. So what would give you ln of 0.1? What is ln of 0.1? And Vav absolutely nailed it. ln can be negative, but the number in it, the a, cannot be negative. And Daria, thank you very much. Yes, we've got negative 2.3. Absolutely. So the value can be negative. So the line can go into the negative range because it's the ln. The number in here, this a, must be positive. Must be positive. Absolutely right. So we can get a negative ln value, and therefore the line can go into the negative range. So it's not a problem at all. Unlike what we have done here with the zero order reaction. In a zero order reaction, this cannot go into the negative range, as I said earlier. So the line would then go on and stay at 0 here. With a first order reaction, it can go into the negative range. And this 0.1, I just picked a value where I know it by heart what the ln is. I could have chosen any other value. Now, we can again turn the whole thing on its head and can say, right, if we plot, for example, if we have a data set, so we have concentrations A, And we have got time. So we've got time and we measure concentrations. And we find that if we plot time versus ln of A, we find that it is a straight line. We know when we do this plot and we get a straight line, we know it must be a first order reaction. So we know it's a first order reaction. There's no other way. If we get a straight line, when we plot ln versus time, or in other words, if we plot the data, we plot ln A versus time, and we get, for example, something like that. Is this a first order reaction? Can this be a first order reaction? The way I've drawn it. Is it possible that this is a first order? If it was a first order, it would give us a straight line. Since this, with the best will in the world, is not a straight line, I can immediately say this cannot be a first order reaction. And the axes are clear. This one is ln A, and here we have time. So if I get a weird curve and not a straight line, and I have got the ln A and time axis, then I know if I see something like that here, it cannot be a first order. It's not possible. Now, there is a question about Half-Life. Now, the other thing is Peter's asking about a second order. Could it be a second order? Yes, it could be a second order reaction. And how we're doing with time? Actually, we could quickly write the equation for a second order reaction. So for a second order reaction, we would have dA over dt equals negative k times A. And what is the exponent for a second order? And you're absolutely right, John. That is exactly where these things come from. What is the exponent that I have to put on the A if it was a second order reaction? So we shall do that, absolutely. To the power of 2. Absolutely right. Now, if you are trying then to integrate this equation, you will find that something very weird happens, because what you will end up with is 1 over A final equals minus k times t. Sorry, I made a mistake. It is positive k times t plus 1 over A initial. So that would be the integrated form. And if we wanted to draw this one for the second order, we would choose our axis, y equals mx plus c. We would choose our axis now so that we write time here on the x-axis and 1 over a on the y-axis, and we get a line like that, a straight line, with this one here being the gradient and the rate constant k. So in a way, this is what a second order or a special case of a second order actually looks like. Now, let's say I've got time values, I've got a concentration, and the concentration goes down. And we plot we plot A over time. And we got something like that. What is your conclusion about this graph? Can it be a zero order reaction? Absolutely right. We can categorically say it cannot be a zero order reaction, because if it was a zero order reaction, we would need to get a straight line. Okay, so then the next step, let's do another graph. Let's plot ln(a) over time. And we get something like that. Can our reaction be a first order reaction? If we see something like that, can this reaction be a first order reaction? And again, absolutely right. It cannot be a first order reaction, because if it was a first order reaction, we would get a straight line. So we can really use these graphs as a more or less a diagnostic tool. Now, let's do the next one, 1 over A versus time. And I get something like that. Can it be a second order reaction if I get something like this? Can it be a second order reaction? Think about it. I told you, if we plot 1 over A versus time, we would get a straight line, wouldn't we? We should get something like that. But actually, we got something like this here, which certainly isn't a straight line. So again, I can exclude a second order reaction here. It can't be a second order reaction, so it must be something different, a different order reaction. Maybe it is a third order reaction, or maybe it is a 1.5 order reaction, or something like that. The M, the order of the reaction, can be any number. So it doesn't have to be a whole number. But I can, when I put these plots down, I can identify, is it a zero, is it a first, or is it a second order reaction? If one of them gives me a straight line, then I know, it is this particular reaction. Does that make sense? I can really use these plots and try to figure out and prove whether a reaction is, for example, a first order reaction. All I need to do is plot ln, concentration versus time, and if it gives me a straight line, I know it must be a first order reaction. Now, somebody earlier, I think Darius, said something about a half-life. And that's an interesting concept, half-life. And since it has been mentioned, let's discuss what is a half-life. Please write half-life, not low-life. I had that in one exam script once. I thought it's absolutely hilarious. No, it's not a low-life, it's a half-life. What does that mean? A half-life actually indicates when our a final is exactly 1/2 of the initial of the concentration. So, and I probably should say, half-life only makes sense for first order reactions. Any other reaction does not, strictly speaking, have a constant half-life. And it actually indicates the time that it takes for a final to go down to half of the initial value. Very often it is abbreviated with T1/2. Now let's have a look at that, what this actually really means. Let's say we have 100, that's our AI, 100 exam scripts, and I want to know, when will I reach half of it? My A final would be 50. Now we can calculate that. We can say, for example, we had our equation ln A final over A initial equals minus K times T. And what I'm now trying to do is I try to figure out what my half-life is. So in order to calculate T, I bring this guy to the other side and I get T, and that would be my half-life, equals ln A final over A initial divided by negative K. Just rearranged. Okay? And according to the laws of logarithm, I can also write this as ln A initial over A final. So this fraction turns round and the negative sign disappears, divided by K. That's exactly the same. So T half-life equals ln. What have I got for my A initial? I have 100 and my final was 50 divided by K. What gives me ln? What gives me 100 over 50? Oh, that's easy to calculate. I don't need a calculator for that. So I need to calculate ln2 divided by K. And ln2, what is ln2? Anyone with a calculator? Yep, it is 0.69 divided by K. That means the half-life of a first-order reaction of first-order reaction is always 0.69 divided over the rate constant, or divided by the rate constant. And that's quite handy, because I can, if I know the half-life, I can calculate the rate constant and the other way around. So I can convert half-life into a rate constant. So for example, it takes me from 100 scripts to 50 scripts, it takes me 5 hours. How long does it take me from 50 to 25 scripts? How long does it take me from 50 to 25 scripts? Absolutely right. It's another 5 hours. If it is a first-order reaction. How long does it take me to 12.5 scripts? And another 5 hours. Absolutely right. So you see, for a first-order reaction, going down to half of the previous value, that is the half-life. And it keeps going and going and going. And can I ever reach 0? So you're absolutely right. Theoretically, I will never reach 0 if I allow for, fractions of scripts. But obviously, that wouldn't make sense a lot of sense in this case. But if you, for example, think about radioactive decay, radioactive decay is a typical example for a first-order reaction. So radioactive decay is a typical example of a first-order reaction. In fact, it is radioactive decay cannot be anything else. It always is a first order reaction. And very often you will find that enzyme reactions are first order reactions, or also the elimination of certain drugs or toxic substances from an organism very often follow a first order reaction. And the nice thing is, if I've got a half-life, I can very easily calculate the rate constant for that. Was it so horrible, the A-level physics? Flashbacks can be positive or negative. So, does that make sense to you? One thing that we need to quickly discuss, what is the unit for K in the case of a first order reaction? So all we need to do is we write our rate law, dA over dt equals minus K times A. And absolutely right. The time, the half-life stays constant in a first order reaction, and only in a first order reaction. It will change if you have any other reactions, zero order or second order or 1.5 order or something like that, then it doesn't stay constant. But in a first order reaction, the half-life is a constant. And let's quickly figure out what the unit is. So we just simply use a unit equation. We just say here, the change, that would be concentration over time, equals K, that's what we are looking for, times the concentration, that's the A. So we see concentration cancels out. So the unit for K, unit for the rate constant in a first order reaction is always 1 over time. So when you see, for example, that somebody gives a rate constant as 1 per second, you know it must be a first order reaction. So it is per second. You can also write it as time to the power of -1. That's exactly the same thing. Okay? Now, let's just simply try and do a little example for that. Wait a moment. I think I need to go over to this one here. Where is it? Yeah. Let's copy that. And okay, so here is a little example. I hope you can see that. And let's see if we can actually apply what we have learned about first order reaction. So in a first order reaction, we already know that's a first order reaction. The concentration of the reactant is 237 millimolar at the start of the reaction. And it's 112 after 27 seconds. Now we need to calculate the rate constant for this reaction. So how are we going to do that? Now we know it is a first order reaction, so it's always a good thing to write down the equation ln A final over A initial equals negative K times T final minus T initial. So that's our important equation. And what we are looking for is this K. So what I always do, which works really, really well, is I create a sort of a little table. So for example, I say my A initial and my T initial. And I have an A final and a T final. So from the given, I just put that in, because if I make this table, then I can very easily extract the information from this wordy text and then plug it into this calculation. So it says the concentration of the reactant at the start of the reaction. So my T initial would be 0. That's the start of the reaction. And the corresponding concentration is 237.29 millimolar. The time is 0 seconds. It is after 27 seconds, that's my final time, 27 seconds, it is 112.09 millimolar. And what I can do now is I can rearrange this equation and make K the subject of that. So I bring this to the other side. I have ln A final over A initial divided by T final minus T initial equals minus K. I bring that, the negative sign, I bring that also to the other side, and I get K equals ln A final over A initial divided by T final minus T initial, and this would be negative. And all I need to do now is I just plonk in the numbers that I just have in my table. So this would be ln A final was 112.09. A initial was 237.29. The millimolars cancel out, divided by negative, I have T final, that is 27 seconds minus 0 seconds. And the 0 I don't really need. So all I need to do is I just simply put that in a calculator. So let's find a calculator here. Where's my calculator? Here's my calculator. So I calculate ln of A final, that was 112.09 divided by 237.29. So that gives me the natural logarithm divided by negative 27. And I get 0.2 0.0277. I hope I've done that all correct. Yep, so that gives me 0.028, let's say. This gives me 0.028 for my rate constant. And what is the unit? Well, we've got the seconds down here, so that would be second to the power of -1. And you see that in this case, k indeed is a positive number, and everything should be good. And now, of course, I can also calculate the half-life. And you're absolutely right. It cancels out the negative. I can calculate the half-life of this reaction, T half, because I know that the half-life is ln, the natural logarithm of 2 divided by k equals 0.693 divided by 0.028 second to the -1. And this second to the -1 is just simply a way of writing for as 0.028 1/2. That's exactly the same, s to the -1. So I can calculate that. And I just simply do 0.693 divided by this value that I had earlier. So that would be roughly, say 25 equals 25. And of course, I have 1/2 to the -1, which is the same as second. So my half-life for this reaction is 25 seconds. So that's my half-life. And that is my rate constant. Does that make sense? Now, I have set up exercises for you on the practice calculation website, where you can calculate, where you can practice calculating rate constants and half-lives. And there's also another type of question where you can actually do something like this. Here is another set of questions where you have a first order concentration of the reactant at the start, and you need to find out what is the final concentration. What is the final concentration? There is a YouTube tutorial how you do that. And the easiest way, again, is with something like this here, with a table. In this case, you don't know your final concentration. That is what you need to figure out. So here would be a question mark, but you have been given the rate constant for that. So I leave you with that. Have a look at the practice calculation website, and I can post a link a little bit later where you can practice these calculations. So I hope this makes sense. Thank you very much. So this is an S. The other one is 25 seconds. Thank you very much for watching, and have a wonderful weekend. And please don't forget to do the test. It is Tuesday, 5 o'clock is the hard deadline. Thank you, be good, and don't do anything I wouldn't do. Cheerio, bye-bye.